Okay, so let's see. We know all this stuff. The temperature at X is 430, right? Kelvins, right? Make sure it's kelvins. And then we're looking at this process here from X to A, okay? So find the temperature at A, right? Now there's two ways to do this. You can look at this and go, well, we're going from 1 liter to 6 liters. And the only way to do that is to multiply the temperature, with the pressure staying constant, right? The only way to do that is to multiply the temperature by 6. So you can do that. For those of you who prefer sort of more formulas and stuff, we're going to use the combined gas law. N stays the same, so it's PV over T is PV over T, right? So this pressure here is 8. Oh wait, the pressure stays the same, that's right. So the volume here is 1 liter, so 1 liter over 430 equals 6 liters. Remember, a 10 to the minus third cubic meters is a liter, isn't it? I think it is, yeah. It's 1,000 liters. And over the whatever that temperature is, right? So that temperature can end up being 6 times 430. So it's 2,580 kelvins. Whoops, 580 kelvins. Pretty toasty hot, you know? All right. Okay, so find the temperature, find the work. Well, work is going to be pressure times change in volume, right? So pressure change in volume, and the pressure is 8 times 10 to the 5th, right? Notice that these axes are, okay, and the pressure stays the same, so we don't have to do anything too clever. And then our change in volume is 6 E minus 3 minus 1 E minus 3, right? Because this is 10 to the minus third, right? Okay, so let's do that. 8 times 10 to the 5th times 5 times 10 to the minus 3. Guess we didn't need a calculator for that. That's 4,000. All right. Okay, and then the delta U. Well, there's two ways to find the delta U. Okay, way number 1 is that U is equal to 3/2 nRT, right? And so the change in U is going to be that times the change in temperature, right? Now, the only problem with this is that we don't have the number of moles, right? I'm going to show you a shortcut, okay? So if you want to, kind of fast forward here, but let's imagine that it's the day of the test and you're like, oh my gosh, I can't remember that other way to find the change in internal energy. What you're going to do is find from the ideal gas law, right? The number of moles is going to be PV over RT, right? And then we know the temperature right there. So we're going to go 85 times 1 E minus 3. I'm just reading off the pressure and the volume, right? And then R is still 8.31. And then T is 430. So I'm just going to find the number of moles so I can use this formula. This is not the way I do it, though, by the way. 8E5 times 1 E minus 3 divided by 8.31 divided by 430. And this ends up being our number of moles is 0.22. That's a 2. Wanted to be a 3. 388, etc. Okay, moles. So now we could do this, right? So our change in internal energy is 3/2 0.22388 times 8.31 times 2,580. That's our final temperature, right? Minus 430. So we're doing 3/2 moles ideal gas law constant times the change in temperature. Let's do that. 3 divided by 2 times the answer I just got, times 8.31 times parentheses 2580 minus 430. And I get 6,000 exactly. Now, you might ask yourself, why is it such around 6,000, by the way, and then like a bunch of zeros and then a 1? Okay? And you're asking yourself, why is that such a round number? Okay? And the answer is that since PV equals nRT, here, I'll write it up here. Right? Notice how there's an nRT here, right? Well, if nRT equals PV, right, then you can actually do this, right? A change nRT here, nR change in temperature equals P delta V, right? Also equals delta P V. So if one of those changes, you can actually do this. This is a shortcut, okay? So let's do the shortcut. Delta U is 3/2 P delta V. It's 3/2. This is a lot easier, isn't it? 3/2 times pressure is 85. Delta V is from 1 to 6 is 5. E minus 3. That's the delta volume, right? So 3 divided by 2 times 8 E5. And of course, this is 4,000, and 3/2 of that, of course, is going to be 6,000. But I know there's some of you that don't believe this. So I'm just going to show you. Oops. Okay. That's not going to do it. Okay. There we go. Yeah, it's 6,000. Right. So then it also says find the Q. Well, let me show you, right? We got a lot of room for this, right? Remember that the heat that flows in is either manifested as a change in internal energy or work. So in this case, we have both, and they're both positive. So our work is 4,000 joules. And since the piston's moving out, that's positive work. Since this thing is increasing in temperature, that's positive change in internal energy. So Q is equal to delta U, which is 6,000, plus the work, which is 4,000. That's going to cost you 10,000 joules, right? So that's going to be your amount of work. All right. Thank you for listening, and have a good day.